This is a dramatic reading of Constructing a Consistent Linear Theory for Gravity, a blog by the Stand-Up Physicist, available at science2.0.com. There is a linear theory for gravity called gravitomagnetism. It starts from the best starting place we have today, general relativity. At the end of my last year's presentation at the 13th Eastern Gravity meeting in Raleigh, someone asked me to compare gravitomagnetism to my own work with hypercomplex gravity theory. Well, I knew they were different, but I had not really dived into the subject in any kind of detail to talk about. So my talk for the 14th Eastern Gravity meeting was to shop and compare between the two proposals. This blog will serve up the meat and potatoes of that talk at Princeton, Friday, June 3rd, 2011, around 4:40 p.m. In my title slide, I did promote science2.0.com. I told the audience that if they found my work interesting, not necessarily right, that they should go visit for a weekly dose of Doug. And I also said that, you know, this weekly blog production was really hard to maintain, but hopefully worth it. So, solutions to the nonlinear general relativity field equations are really hard to find. We focus our attention on the few that have been found decades ago. And working with those solutions is darn difficult. Much of the time in the 2 days of those talks was devoted to struggles with numerical solutions, because those might provide signals for a gravity wave detector to find. Now, faced with such technical challenges, it might be easier to work with linear field equations. We live in a nearly flat universe. Now, why not model such a universe as being totally flat with just a small perturbation? Now, that's what is done. Construct a wave equation for flat spacetime with a perturbation. And you choose a transverse gauge because that makes the equations take this following simple form. There we go. All right. Now, that where the H is a perturbation and that funny Greek letter is a flat metric. It looks darn similar to the Maxwell equations written in the Lorentz gauge, which I wrote just below it. Now, the big difference between the two is the rank of the equations. Now, I don't understand quite the details of this move, but those well-schooled in these kinds of subjects say that we're really only interested in the retarded solutions. And this allows us to focus on these kinds of terms, where yes, we have a J and a rho and a phi and an A, just kind of like normal sort of stuff. But I should say those J's and rhos are about mass density and mass flows, or matter current, really. So, so this equation will be constrained to work actually now to just low densities and slow moving stuff. And with all those assumptions in place, we can write out the gravitomagnetism field equations like so. Alrighty, let's see how close we get that. Alright, and you know, you look at this and you go, wow, that really looks familiar. That looks like the Maxwell equations, you know? And I actually kind of got upset when I saw this. Because, you know, learning physics on my own has been just a slow, difficult process. And my studies have all centered around special relativity, the Maxwell equations, gravity, and quantum mechanics. ignoring other perfectly fine subjects such as solid-state physics or chaos theory. Now, I learned by doing and making lots of mistakes. And these equations actually reminded me of mistakes I had already made trying to construct a theory for gravity. Now, let's take the big picture view. Now, how are these four equations of gravitomagnetism different from the Maxwell equations? Now, I know they're like a factor of a half here and there to satisfy the spin two gods. No. But gravitomagnetism field equations are just like clones of the Maxwell equations, and I'm using the word clone with a negative kind of spin. Such clones are evil because for gravity, like charges attract, whereas in EM, like charges repel. Now, I could spot four fatal flaws. The E and B fields can be written as an antisymmetric rank 2 tensor. Now, changing the order of the indices flips the sign, and that is the sign of a spin 1 field. And for spin 1 field, like charges repel. Bullet in the head, number 1. Now, to get the currents, there would need to be a vector current coupling term in the Lagrangian. And that would be that JA sort of term. And if you spend some quality time with good old Feynman here, oops, chapter 3, he'll teach you, he will, that that means that the force, the particles involved must be spin 1. And spin 1 means that like charges repel. Bullet in the head, number 2. Now, a metric is a symmetric thing. And gravity is all about changes between two symmetric metrics. And those changes will be symmetric. So that cannot be kind of accounted for using an anti-symmetric field strength tensor. Bullet in the head, number 3. So there are actually no monopole, the no monopoles law for gravity would mean that there would be like 2 poles for gravity source if you just started shaking one up. And that actually would have like charges that could both attract and repel, and that also kind of means that there should be 2 signs to mass charge, and we've only ever seen 1. So I call that bullet in the head, number 4. In fact, I was so upset by my initial study that I emailed a professor who had written a brief review of the subject. And he was very polite in responding to me, and he assured me that these problems were already well known. Now, this was actually a relief, because it meant that I had a good self-education. Those fatal flaws are accepted because the linear perturbation of general relativity is useful. So professionals understand the limitations of this approach. This is a toy theory. Now, toy theory as a label sounds too generous. I mean, I think it should be called a broken toy theory. I object to calling it a linear perturbation of general relativity. I mean, the label implies that the equations result in a linear approximation of general relativity. Now, a valid linearization would chop off the nonlinear parts, but would not introduce any new problems. But gravitomagnetism introduces these fatal flaws. You know, if something is broken, I say fix it now. Now, this is actually an attitude I got from my time at the bench. Nature just doesn't care if you get things wrong. And she also doesn't care if you keep on going down that wrong sort of path. So my correction involves forming a Lagrange density using hypercomplex products. A Lagrange density is every way that a system can interact per unit volume. And then by taking different derivatives, you end up getting things like the field equations or the stress energy tensor. Now, that hypercomplex thing, that sounds scary. But it's actually a simplification of familiar things to people who have exposure to complex numbers and to vectors. So what you do is you start with the complex multiplication, and then you make your imaginary I into imaginary 3 vector that's got an I, a J, and a K. And what all you need to do then is include the cross product. Now that basically makes the rules for quaternions, all right? And to go from this rule of multiplication of quaternions to hypercomplex numbers, you just eliminate any minus sign you see along the way. So like the Lagrangian from the Maxwell equations, there is going to be a current coupling term, and there's going to be derivatives of a potential. In other words, the same players take the same stage, but they do a different kind of dance since the rules of multiplication have been altered. And here is my hypercomplex gravity Lagrangian. Every term that appears in the EM Lagrangian also appears for the hypercomplex Lagrangian. The 2 cross terms keep their signs, but all other flip their signs. So you generate the field equations in the standard way by applying the Euler-Lagrange equation. To make Gauss's law, you take the derivative with respect to phi, and there is Gauss's law, well, with 50% of the signs changing. Notice that the ones needed for Newton's law of gravity were the ones that changed signs. And Newton's effort suffers from the problem that a change in the mass density would have to propagate instantaneously. These field equations, on the other hand, do not have that flaw since there is a time-varying term. The same sorts of exercise can be done to generate Amperes Law. Here again, 50% of the signs change. This is important because it means that Amperes Law for EM is distinct from this proposal for gravity. Gravity has but 1 charge, so it should be distinct from EM, which has 2. There are no hypercomplex gravity monopole law or Faraday's law, those so-called vector identities. I would consider that a good thing. I mean, masses look like gravitational monopoles. Shake an electron up, and there are 2 poles. And that's actually a sign that there are 2 types of electric charge. Because in a different reference frame, they wouldn't have any magnetic field, but they would have different charges. So shake up a mass, and there will be an effect, okay? But there should only be like an attraction going on, since there is only one sort of mass charge. After all this time thinking about the issue, I think I can finally pinpoint where this kind of problem arises. The linear perturbation of general relativity in this equation, that would be, yes, that one. Okay, that's does have a spin 2 field. That can be seen because what you do is you vary the mu and the nu there, and it wouldn't change its sign. So that's actually an excellent thing. It's only when they say, oh, I just want to focus on this one sort of solution and go from a rank 2 field equation to a rank 1 that the problems really are generated. I mean, after all, you're going from like 10 field equations like down to 4. And that's going to have some serious consequences. It is these 4 equations that are known as gravitomagnetism. So I am at peace with the linear perturbation of general relativity, but not with gravitomagnetism, the broken toy theory as I refer to it. I posed the audience of about 40 folks a question. How does this work affect you? And I said my unified field theory actually predicts that the LHC will see no Higgs and not a single SUSY particle. Given the time limitation, I wasn't actually able to go into detail about that issue, about not needing a Higgs, but I've covered that in an earlier blog and an earlier video. So if the LHC does find a Higgs boson, or one or more SUSY particles, then my work is wrong, okay? And such a discovery would actually save me about $500 from visiting the 15th Eastern Gravity meeting, which is being planned for Syracuse. Now, while it would be kind of disappointing to be wrong, I mean, I can't feel that bad, because unifying gravity with the other forces of nature is just a really difficult job. So failing at a tough job, it's actually to be expected. Now, if the LHC does not find the Higgs boson, or one or more SUSY particles, and basically, if the LHC does what every other collider experiment has done before it, then this hypercomplex gravity and GEM unification proposal might be right. I mean, it's not wrong. It's got the chance to still be right. So here was my final slide. I pointed out three things about the GEM unified field equations. One was the lack of a unified current. In EM, like charges repel. For gravity, like charges attract. Now, since one cannot have a charge that both attracts and repels, well, when the two are united, there's actually no current density. Now, to make the equation dimensionless, I needed an area. So I just plucked in the Planck area, which has units of relativistic, that's C there, quantum, the H bar, gravity, G. Now, my goal was to make things dimensionless, and yet I end up with a relativistic quantum gravity expression that Poisson himself would have been familiar with. The final observation was about the ability to choose a gauge. Now, this is a vital issue at the Lagrange density level. Generate the field equations and then pick a convenient gauge for the problem at hand. Now, that is how it works in EM. That is how it works in general relativity. With the GEM proposal, both the Lagrangian and resulting field equations are invariant under a gauge transformation. Changing the gauge doesn't change my field equations like one iota. If someone, seeing this actually wants to reflect on what that means to have field equations that are invariant under a gauge transformation, please contact me. I'd like to hear what you have to say. Now, we know that electric charge is conserved. We know that 3 weak charges are conserved, and we know that there are 8 strong charges that are conserved. We associate the symmetries U1, SU2, and SU3 with each of those conserved charges respectively. It is natural to suggest that we therefore need the tensor product of these 3 symmetries. And that means we need a Lie algebra with these 12 elements. Now, based on discussions that happened on Science2.0.com, my initial efforts to create that tensor product with quaternions just, failed. And I was, forced to admit that I actually was using this kind of hybrid thing, tensor product of U1 and SU2, but then I was kind of using SU2 as a subgroup of SU3. So it was like, well, I finally decided that I really didn't have electroweak symmetry as I had hoped I would, and I actually shifted to the view that of looking at U1 as just being a subgroup of SU2, which is also a subgroup of SU3. Now, if one can write a Lagrangian with SU3 symmetry, it necessarily has SU2 symmetry. It necessarily has U1 symmetry. And that might be all a Lagrangian needs to cover the symmetries found, and symmetries and thus the charges in the standard model. So that would need all of 8 generators for the Lie algebra. You know, making things smaller is just not the direction like most folks work in. Supersymmetry folks working in SU5 and SU10, and some newer work going on with the monster group E8. Now, am I really serious about not going to the 15th Eastern Gravity meeting if the Higgs is found? And that's a definitive yes. You know, my family can easily consume the money on more shoes or car repairs. I feel uneasy about my field equations, as they would call into question, you know, every bit of work done with the Einstein field equations which is just an enormous amount of effort. So go LHC, go! Vote up or vote flat, you know. No, I got that wrong. Vote down on my theory, or say, well, it still is viable. All right, so here is my snarky puzzle. Write out the Maxwell equations in the Lorentz gauge. Write out the hypercomplex gravity equations in the Lorentz gauge. That was actually on the last slide. Now subtract the first equation from the second. Shop and compare with the GEM unified field gravity and standard model symmetry field equations, also written on the last slide. And reflect on how important it is to be similar, but not quite the same. Thank you very much.